Welcome, I'm Salvatore and I'm going to present our work about transparent caching for RMA systems. So, let me start with a motivating example. In the n-body simulation, we have a system composed by n entities, the bodies, and we want to simulate how they interact over time, and in particular how this interaction changes the speed, for example, and the trajectory of these bodies. Now, if we want to parallelize this simulation, we can model like these entities in a 3D space and using an ocт tree to model them, or like in this case, in this more simple case, in a 2D space and by using a quad tree. So here is the space we want to model, and this is the quad tree that we use in order to represent these points. So the idea of the quad tree is to keep splitting the space until we have, for each leaf, just one body. So, and like this is an expansion, a particular expansion of this tree, and this is like the one partition of this quad tree. So now, if we parallelize this, we could assign this partition to a specific processor, right? And this processor will be in charge to compute the interaction of the bodies that are assigned to it with respect to the others that are outside its partition. So, for example, we start from this point here, and in order to compute its new speed and trajectory in the next iteration, we will need to access all the points in this gray area. So this is just a high-level example to show the idea. And then, when we move to the next point, so like this, you can see that basically the points we are accessing are more or less the same. So it makes sense to cache those points in order to avoid to access them, to make like remote accesses in order to read their information and avoid that this is performed twice. So our first observation is that it could make sense to actually cache data for a particular class of application. And this is like a real example. This is still quite small, like 4K bodies and 4 processes. But it shows that already for this small example, the same get here, these are the gets. So one get is repeated like more than 2,000 times. And like there are 60 gets that are repeated like 4 times. So these are exactly the same gets accessing the same data. So this can be avoided. These multiple remote accesses can be avoided. So this is our first observation. And now the question is, okay, but if we cache this data, can we actually gain something from this caching? And in order to answer this question, we need to see a bit how an architecture of a modern supercomputer looks like. So we have the supercomputer that is composed by multiple cabinets, and then for each cabinet we have multiple chassis, then for each chassis multiple blades, and then nodes, and then finally the cores. And the question is, okay, does it change something if we access data between cores or between nodes or blades or among different chassis? And like this benchmark shows this data. So here we report the time of an MPI get as function of the data we are requesting with this MPI get. And we report it for different levels of this hierarchy. For example, the red line shows the time of this MPI get if the two processes, the initiator and the target, are mapped on the same node. So it's accessing among cores. While the violet line is showing the same experiment, but this time they are on different nodes. So same blade in this case, different nodes. And then here we are on different chassis, but same cabinet. And finally the blue line is among different cabinets. So we can actually see that there is a lot of space here. There is like an 10x that we can gain by avoiding this internode, these off-node accesses, and just transforming them as local accesses. So, and this will be like the aim of caching these remote accesses. So just transform them from off-node accesses to in-node accesses. And here we are showing like the data, this data up to 64 kilobytes, but actually this trend keeps going also with larger data, like 10 megabytes. We can still see that there is a 10x difference between the intranode and inter-cabinet access. So the second observation is that, yes, if we cache this data, we can actually gain something in terms of performance. So, and driven by those observations, we start thinking, okay, how can we design this RMA caching system? And in particular, we target MPI-3. So in MPI-3, we have these remote memory accesses where communications are can be one-sided. This means that the target process is not aware of the communication that is going on. These are the operations that are available, and the idea is that you have epochs, and in these epochs there is no synchronization. So within an epoch you can have multiple operations, and then you can have synchronization only when you explicitly require it by closing the epoch or by forcing it with specific calls. So during the epoch you can just assume that your RMA operations are in flight and nothing else. Since we want to target MPI-3, we made some design choices, and in particular, first of all, we choose to handle variable size cache entries, because with a get you can request data of any size, so we have to handle variable size cache entries. Moreover, we decided to cache only get operations, and this choice is dictated by the MPI specification, basically, because you cannot have multiple puts within the same epoch, but targeting the same data. So this means you can have multiple puts, but the data you are writing to has to cannot overlap. So we cannot prevent like remote memory accesses or remote memory writes in this case. Also, you cannot have puts and gets targeting the same memory area in the same epoch. In this case, the outcome of this operation will be undefined. So this is why we choose to cache only get. Obviously, the framework can be extended in order to cache also accumulate operations. The one important design choice is that the data has to be copied into the cache when the epoch closes. And I mean, this choice derives by the fact that we want to build this framework on top of MPI and not within MPI. Hence, we need to comply with this specification that says that we can be sure that the data is arrived only when the epoch terminates. As a consequence, only at that time we can make the second copy, like we can make the copy in our caching system. So we introduce an additional data copy stage here. Okay, so now the question is, how do we interface the user applications to this caching system? So in particular, we provide 3 modes. So transparent, always, cache, and user defined. And these modes can be specified as through the MPI info object or passed to the MPI win create call. So whenever you create a window, that is the mechanisms that MPI uses to expose the memory, to let processes to expose the memory on the network, you can specify which mode of this system you want. So for example, you can use the transparent one to enable any application using RMA accesses, to enable caching on any application using RMA accesses. In this case, we just need to invalidate the cache at every epoch. So whenever an epoch terminates, we need to invalidate the cache in a way such that we can comply with the MPI specification. So in this case, we see that we have the 2 processes, P0 and P1. P0 is making some requests towards P1, and in this case 0, 1 and 2 are misses because they are not in cache, and then whenever you ask 0 and 2 again, you will get a cache hit, and you can avoid to make a new remote memory access. And here with this bold arrow here, we close the epoch, and hence we invalidate the cache, because this means that at that point some writes can concretize on the remote memory window, and hence we need to invalidate our cache in order to get the up-to-date data. Okay, and then we can have different epochs. The always cache mode is different. It's the case where you have a data structure and the user ensures you that this data structure is read-only. You can think to a graph, for example, where the structure of the graph is defined and you are just analyzing it and not writing or modifying it. So in this case, the cache will never be invalidated for the whole duration of the MPI window. So even if you close the epoch, the cache is still there, and you can have more hits in this case. The third mode is the user-defined one. So this is like a case we then use also in the Barnsat experiment, and the idea is, okay, if the user can tell us that I'm sure that for this number of epochs, my window will not be written by me, by my process, or by any other process. So for those number of epochs, the cache will be, the window will be read-only. So in this case, you can just have, like here, you have 2 epochs, and in these epochs, the cache is valid, and then once like an application phase terminates, like you can think to a BSP model. So here this phase terminates, and after this phase, this guarantee that the window, that the data represented by that window is read-only doesn't hold anymore. Hence, you need to invalidate the cache manually. And for this, we introduce a new call that is the CLaMPI win cache invalidate, where you just pass the MPI win that you want to invalidate. So, but what CLaMPI stands for? So CLaMPI stands for a caching layer for MPI. And since we are defining a software caching layer, we need to define 3 main building blocks that are the indexing of the cache entries, the storage of the cache entries, and how do we perform the victim selection when we need to evict some entries. So let's start with the first one, the indexing. For indexing, we use an hash table and the Kuko hashing for resolving conflicts. Just to recap a bit, with Kuko hashing, we have 2 tables, T0 and T1, with their hash function, H0 and H1. Now, whenever we want to insert a new element, so like we want to insert A now, we start with H0, we compute H0 of A, and in this case, we get 1. But 1 in T0 is already occupied by X. So in this case, we will just swap X and A, and then try to insert X in T1 by computing its hashing with H1. So we get 3, and then we swap again, and so on. In this case, then we get 4 for H0. This means that Y will be inserted in this position here, and the insertion will terminate, will be successful. So now this is just a small example, but this scheme can be extended to multiple hash tables, Kuko tables. And but the question is, okay, but what if we keep this sequence keep going? In this example I showed here, I was just lucky because after 3 insertion I stopped because I found an empty entry in T0. But what if this is not true? So normally in Kuko hashing, when this happens, you just invalidate everything and change your hash functions and rehash. So this is one strategy to fight this problem. But this, in our case, could lead to a too high overhead. Remember that the idea is to like build a low overhead caching system. So instead of doing this, we just consider an access that leads to a sequence of insertions here in the Kuko hashing that is which length is above a certain threshold as a conflicting access. So once we detect these conflicting accesses, so too many swaps, basically, what we do is just we evict one of the entries in this sequence, in the sequence of the visited entries, by this insertion procedure. So a conflicting access is defined as an access that caused a miss and also caused an eviction in the hash table. Okay, so the second step is how do we store the data? So in order to store the data, we use a memory buffer. So this is just a contiguous area of memory, and this allows us to avoid like memory allocations on the fast path, and also it helps prefetching because we keep the data cache line aligned. Also, we keep the free regions of this memory buffer in an AVL tree, so we can have low overhead in the search of this free region. And in case we don't have any free region, then we will have a capacity access. So similarly to the conflicting access, a capacity access is an access, so a get that has been found missing, and it caused an eviction due to capacity, so because there was not enough space. So in conclusion, in general, this is the architecture we have. We have MPI and then the application, and then in the middle we have CLaMPI that is relying on these data structures in order to enable RMA caching. Okay, so, but here actually there is a problem. The problem is that using this memory buffer, the use of this memory buffer leads to the fragmentation, to a fragmentation problem, an external fragmentation problem. So how to fight this? So the idea is to rely on the victim selection procedure in order to decrease the fragmentation. In particular, we introduce a new score that is called the positional score, and the idea of this positional score is that it estimates how bad an entry is cached, is stored in the memory buffer. So like how much this entry is contributing to the external fragmentation. And then we used a combination between the temporal and the positional, where the temporal score is just an LRU-like score, so just for estimating the reuse probability of that entry, in order to perform the eviction. In particular, here we see an example, and here this entry here will have a very bad positional score because it has some free space on the left and on the right. So by evicting this entry, we will gain all this space to store a bigger one, while these ones are okay because basically they don't have free space. So the positional score is proportional to the free space that is adjacent to the entry. And like this is an experiment where we show the fraction of the space that is occupied as function of the time. So like this is how the number of gets that are executed by the experiment. So like this is the time, and you can see that if we use just the temporal score, the occupied space decreases because we have the external fragmentation. While if we use the positional or the full score, where full is just the combination of the two, we can keep a higher occupancy of the memory buffer. So till now we said how do we score, how do we rank the entries in order to evict them, but actually how do we select the entry to evict? So the idea is that, remember that always the point is to have a low overhead caching system. So the idea is just to sample the data, the cached entries, and then select the victim within this sample. So the sample is performed on the hash table. So we said that we have this hash table to index the entries, and the idea is that we just start from a random position inside this hash table. We sample a number of k entries in this hash table, and then we perform the victim selection among those victims. So this implies that the quality of this sample is related to the size of this hash table, and in particular to its utilization factor. So you can imagine that if you have a really large hash table with respect to the number of entries that are actually stored, you will have a lot of holes in this hash table, and hence your sample will be, the quality of the sample will decrease. So, and this experiment actually shows this phenomena, and here we have the same, we fix everything, so we fix the workload, we fix the memory buffer, and we just vary the hash table size. And here you can see that by increasing the hash table size with respect to the workload, the quality of the eviction will decrease. And as a consequence, also the number of hits, because now you are evicting kind of random stuff, and this is not good, and this is shown by the number of hits that is decreasing in this plot as the hash table size increases. But still, this plot also shows that by using the full positional score, we can keep a higher number of hits with respect to the temporal positional score, and also here we have like the amount of free space, the fraction of free space, and we see that while temporal, that is just the LRU-like, so doesn't consider the external fragmentation problem, as a higher fraction of free space because of the external fragmentation itself, we can lower this free space. So this means we can use the memory buffer in a more efficient way by using positional or full. But still, we can see that even if full has more free space than positional, because it takes into account also the temporal score, it still has a higher number of hits because it takes into account also the temporal score. Okay, so at this point, this is time for some timings from some numbers, and in this experiment we show like the runtime of a simple experiment. So this is just 2 nodes and one process is performing a number of gets according to some distribution towards another node, and we compare MPI versus CLaMPI. And again, this shows the problem we were discussing. So by increasing the number of entries with respect to the workload, you get a variation in the performance of CLaMPI. So in this case, this is like the optimal for this experiment. So in terms of hash table size, and then it starts increasing again. This is not shown on this plot, but also if you have like a too small hash table, then you will have a lot of conflicting accesses, and then the performance will be not good as well. So we are not very satisfied at this point because we need to like tune the exact hash table size in order to actually have a nice improvement with respect to MPI. For this reason, we introduce another scheme that is called CLaMPI Adaptive, and the idea of this CLaMPI Adaptive is just to monitor the occupancy of the hash table and on the memory buffer, and like resize the hash table and the memory buffer on the fly. So in a way such that we can converge to the optimal number of hash table entries or data sites for the memory buffer. So the bad point of this scheme is that every time we want to adapt, we need to invalidate the cache. So this could cause some overheads. Finally, some benchmarks. So we tested the system on the Pittsdale supercomputer, that is a Cray XC50XS40, and with Dragonfly, and we compared to FOMPI, that is the fastest MPI-3 RMA implementation available on this machine at the time of these experiments. And the first question that we ask ourselves is, okay, did we match the requirement of low overhead? Is this software caching system really low overhead? And in this experiment, that is again like a kind of ping pong between 2 processes, we show like the time, we show a breakdown of the causes, and for different accesses. So this is like an hit, this is a direct access, where a direct access is just a miss and that didn't cause an eviction. And then we have conflicting, that an access that caused an eviction due to conflicts in the hash table capacity, an access that caused a miss because of the space, and failing if an access causes a miss, but after that miss there is still not enough free space to store that data. So in this case we don't keep evicting entries, but we just fail. And failing means we just fall back to the normal get. We just get and don't cache the data that we actually get. So here we show, like, for comparison, the 25% of FOMPI, so this is like the non-cached data, and we show that like the hitting, the lookup in the hash table is always constant, and this is thanks to the Kuko hashing. And then we have like the eviction that increases with the capacity, because here you have actually to look for the sample and find the victim among the entries of that sample. Finally, we see this data copy phase. This is the additional data copy that we introduced in the beginning. And here, this is not very nice, because every time we need to like make this second copy. And like a future work could be to offload this data copy to like a NIC, like the portals for enabled NICs, and in a way such that we can actually mask this cost and overlap it to computation. Okay, then we have an evaluation of the BANSAT. So this is the n-body simulation using the BANSAT algorithm. And like the first plot here shows the finding of the optimal configuration for CLaMPI. So, and in particular for CLaMPI fixed, so not the adaptive scheme. So here we vary, in each tile, we vary the size of the memory buffer, so 1 mega, 2 mega, and 4 mega, and then also we vary the hash table size. And we show the time to perform the force computation phase of this algorithm. So we also compare against a native cache implementation that we found in this benchmark, and as expected, I mean, this native cache implementation is directly mapped, so is independent from the hash table size. It is just affected by the size of the cache that we dedicate to it, and as expected, it decreases with the cache size. Then we show the CLaMPI fixed, that is the green line, and we see again that if we use a too small hash table size, then we are getting a lot of conflicting accesses, and this leads to a bad performance. In this case, it's comparable to the native cache that we found there, while the adaptive scheme is basically independent from the hash table size because it can just adapt itself. Finally, we show a weak scaling experiment, so that compares CLaMPI fixed and adaptive with native and FOMPI. So while in the second part we show the weak scalability experiment, where we vary the number of processing elements and we show the force computation again as function of this number of processing elements. Here we have that CLaMPI fixed and adaptive are basically performed from 3x to 5x better than native and FOMPI respectively. And both the CLaMPI configurations are the same in this case, simply because we just start the CLaMPI fixed from the optimal parameters that we found in this initial study. The second experiment is the local clustering coefficient. So here, again, we have two phases. So this is here we use the always cache mode of CLaMPI because here we have just this graph and this is read-only, and we want to compute this coefficient on this graph. So again, we have like the first stage, that is the parameter study, and here we again vary the number of the size of the memory buffer and the hash table size in order to find the best configuration for CLaMPI fixed. Again, you can see that CLaMPI adaptive performs always the best in this scenario, and hence we have the weak scalability. And we show that while CLaMPI fixed at certain point start scaling worse, CLaMPI adaptive is able to adjust itself. In particular, is able to adjust the hash table size and the memory size in a way such that it can keep a good scalability. And the main reason of why here the weak scalability kind of stops is because of the nature of this algorithm, that once you spread your the load on multiple processes, then you lose the locality, and then hence the effect of caching disappears. Okay, so to conclude, we started from two observations. The first one is that there is a class of application that is actually presenting data reuse. And then the second observation is that yes, we can actually gain something from caching these remote memory accesses. And then we present CLaMPI with its three main building blocks: indexing, storing, and eviction. And finally, we show some evaluation of it. You can find more of it in the paper. The source code is available on GitHub, and I'd like to thank you for your attention.